Okay. Now, last day, if you remember, we came up with confidence intervals for probability. Today, we want to come up with confidence intervals for the mean, and on Thursday, we're going to come up with confidence intervals for the standard deviation. Those are the only three things that we ever measure: the p, the mu, the sigma. So what would be the point of finding a confidence interval around the mean? This is simple, okay? We want to find the average height of a Mesa College student. Let's say that's our goal. And we do really proper sampling. And if we're lucky, we can do a really huge sample, because we know the bigger the sample, the more accurate. But the other thing is, bigger the sample, the smaller the error is, that whole plus or minus. We're going to figure out how to calculate that. Because let's say, for example, okay, let's say, for example, Lila wants to open up a clothing shop on campus. And you want to come up with maybe the sizes of clothes that fit, the majority of the people. Well, let's suppose our campus, we're really close to Hobbiton, and like in Lord of the Rings, and our campus is really, really small people. Primarily everybody on campus is like 3.5 feet tall. Well, we'd probably want to market a line of clothes that were really small. Let's say we live, right next to Johnsonville, and everybody on campus is Robert Small compared to everyone on campus. Okay, we probably want to design clothes that are absolutely huge. Or let's say the average height of a Mesa College student is, 5'6", just throw out a number. Well, we would probably then design clothes so that that person is the most likely person to buy our clothes. So we would want to market our clothes to that person who's sort of the average height. Then if somebody's a little bit bigger or a little bit smaller, we would still fit them. See, if you're wearing a medium shirt, is there only one size human being that fits a medium, or is there a whole range of people? Yeah, there's a big range of people. And when you get out of that range, then you go to large and so on. So there would actually be, from a business standpoint, there is a lot of reasons why you would want, not the average height, but the confidence interval around the height. You'd want to know what is the range that you're dealing with. And so what we do is we would collect information. We would collect from a given sample size, we'd collect X bar and we would collect S. We would collect the sample mean and we would collect the sample standard deviation. We don't know the population mean. We don't know the population standard deviation. By the way, make it real simple. Last day when we were doing confidence intervals around P, like we were using Rosalind's free throw shooting ability, if we actually knew the value of P, we wouldn't need to collect any samples, would we? We would, if I knew absolutely what percentage of free throws you make, period, then I don't need you to shoot any for me to figure out what your likelihood is. But that's not realistic. If I absolutely knew that denarii that I found, 2,000 years old, I found it buried in the dirt in Rome, right? It's got the picture of the Caesar on one side, and it's kind of rough, not perfectly round. I would not assume that is exactly a 50-50 coin. But let's suppose that I knew absolutely that it was. Well, then would I need to flip it 1,000 times to figure out the probability of a heads or a tail? No. So basically, you don't know what P is. That's why you did sampling. That's why you did an experiment over and over again. Well, similarly, if I have a population, I could figure out the average height of everybody in the United States if right now, today, I measure everybody in the United States. But that would be easy, right? There's only 340 million people. And who's going to do the measuring, by the way? And how many people do we have to measure, or do we need to do the measuring? Because 340 million people, I'd probably have to have a pretty big staff, wouldn't I? In fact, if I had 1,000 people working, that means each of them are going to measure 340,000 people. Well, aren't there people that are still growing then? So by the time I'm done measuring everybody, haven't some of those people gotten taller because it took so long? So realistically, could we possibly know the average height of all human beings or all Americans? No. So we would take a sample and we would construct a confidence interval. You take samples because you probably can't know the population. So we went out and we collected a sample. And so what we want to do is say, all right, we want to calculate, we want to calculate the error. We called it big E last day. Now, last day our error was a probability because that's what we were measuring. Today, our error will be involving the mean. So error has units, by the way. So if we're finding average height, for example, then my error would be in the height units that I'm using, maybe centimeters, maybe inches, something like that. So we would need to calculate the error. Now, on your formulas, I'm going to go ahead and bring that up right now, because not everybody has this in front of them. Hey, come on. I just want to take so long. There we go. Bring this up on the screen because I want to show you guys where it is and how to do it. We're going to do a whole bunch today. There's nothing complicated about this. It's actually quite simple. All right. There we go. Here we go. All right. Let me get out of this screen a bit. The Desmos screen going here. Previous instructor left their stuff on here. Huh. Oh my goodness. I really should close this out. All right, now let me do this. This is, you know what, I might not be able to get in there. The previous instructor has got this. It won't let me get past the previous instructor has set up the look so that it goes directly to their whatever. I've never actually seen a screen like this in my entire life. Say again?
You can use a different browser.
Well, Mesa College doesn't really like it. I'm trying Firefox. It doesn't like different browsers. That's
It's on his own.
On his Google.
On his Google?
There we go. Well, let me go. Yeah, that's. I don't like using a different browser because then it'll say things like, "Well, do you want to make this the default browser?" I'm like, no, I don't want to. Okay. Yeah, really, I should log out. Oops. Try that again. I have fat fingers. I usually hit 2 keys at once. I do a lot of that. All right, now here we go. Little, there we go. The previous instructors who use this don't actually realize there are other people who use the room. Bless you. Okay. All right, now finally, here we go. Hey. This you should actually have with you at all times, and I know everyone doesn't. It's like the Z table at all times. Okay. There we go. All right. So we know all these formulas at the beginning. We use those for the first test, and we have a whole bunch we use for the second test. And now we have a whole bunch that we're using currently. Now, normal distribution, of course, we know that if it's a sample of size 1, n is 1, no big deal. But if it's a sample of size n, we have to divide by the square root of n. We've got the common z's, these guys here. Okay. Now, this is what we did last day right here. We set up a confidence interval around the true p. Right? You went out, we shot a bunch of free throws and said, what is the actual p? It's going to be a plus or minus. The error was the key term. The p hat was what we measured. That's kind of like X bar. X bar is our sample mean. X bar can't be the population mean. I'm going to go out and measure 25 students and have that represent all of Mesa College. But what are the chances that I hit it exactly? Well, actually, it's not. That's really not a possibility. So now we get to here. Hold on a second. Hold on, where's my oops, here we go. Here's my E is right here. For there, highlight this row. Now you see, I want to find the true population mean of a sample, or excuse me, the true population mean as an interval only having a sample. So I know I need to do a plus or minus. So it's going to be, really in real simple terms, it's going to be X bar plus whatever the error is, and X bar minus whatever the error is. Now, what did we do last day? We said the p-value was between the measured p plus the error, the measured p minus the error, right? That's what we did last day. We calculated the error. The measured p, that was our sample. That was what p hat was. That was Rosalind went out and made 80 out of 100 free throws. So we used that as our starting point. So this is a probability. This was a plus or minus probability. This is now measurement. It might be height units. It might be weight units. It might be money. Whatever it is we're measuring, I'm going to take my sample like this guy, and I'm going to add and subtract the error. But now the error is in terms of whatever I'm measuring. This is not probability anymore. And so the error that we're going to use is right here. Now, remember the Z alpha over 2? We want to construct a 95% confidence interval, a 99% confidence interval, a 90% confidence interval. That determines what Z value we use. That's one of those magic number Z's we talked about. But then look what else it is. It'll be sigma over the square root of n. Now, do we know sigma? No. So we'll use S. We don't know sigma. If you don't know the population mean, do you know the population standard deviation? Probably not, because you need the population mean in order to calculate. Does that make sense? So we would actually use whatever we have. So let's do a really simple example. You went out and from a population, a large population, you collected a sample of size, let's say 60. Your mean of your sample that you collected, let's say is, what do you want to collect? Let's say you wanted to find out, say again? Pennies? Like how many pennies people have? Okay, you went out and you asked 60 people how many pennies they have in their pocket. That's a fun one, okay? And you found out that the average number of pennies people have in their pocket is 47.8. Now, wait, that's probably absurd, but you know, we have people that like to collect pennies, let's say. And we had a standard deviation among that group of 11.32. It is normal to take the standard deviation a little bit further than the mean. It is normal to actually go one extra decimal place. So what I want to do is I want to construct let's say a 95% confidence interval for the true value of the mean. I don't know what mu is. I can't know what mu is. All I have is a sample. But what I can do is say, if I take a large enough sample size, the error will be small. And so my plus or minus will be small. And we can say with 95% confidence, or in other words, of all the samples that exist, 95% of the time, we're going to hit it right on the button. We're going to nail it. Is it always possible that your sample is extreme? Is it possible? Yeah, you don't know, but it's always possible. If I have a 95% confidence interval, then it's 5% likely that I miss the mark. But 95% I'm pretty certain of. So what Z value do we use in this case? Remember, if it's a 95% confidence interval, that means 95% lives here. So 5% lives in the tails. So there's 2.5% in each tail. Well, so that's why we say, oh, I want Z of 0.025. That means a Z with a 2.5% tail. And what was that number? 1.96 or 1.960, and that came from here. These are the ones that we looked up. I didn't tell you these. We looked these up in the table. They're computer generated values. You do not need to memorize these. But if you do a lot of problems, you actually will remember them just because you keep using the same numbers over and over and over again. So for this problem here that we're looking at, I want to construct this confidence interval. So what is E in this case? Let me go back, bring it back up again. I'm gonna write this down. The E we're gonna use. Hold on, where? Oops. Oh, here. The E we're gonna use is right there, except that we have S rather than sigma. We don't know what sigma is, so we have to use our sample. That's one of the reasons you want to take a big sample, because you're also dividing by the square root of n. The bigger the sample, the bigger the denominator, the smaller the error. So what would be better, 60, a sample of size 60 or a sample of size 600? What would be better, a sample of size 60 or a sample of size 600? There's no exception. Bigger sample, better. Absolutely, always, every conceivable situation. There's no such thing as a small sample that's good. Small sample is bad. Bigger sample, better. But you might not be able to get a bigger sample. So you get, the rule of thumb is you get as big a sample as you can get. Remember, talk about time and money. Time and money are the things that determine how big a sample. So let's calculate the E. Remember, we need this. So the E is 1.96, okay, times 11.32 over the square root of 60. Okay, that's the Z, that's the standard deviation, that's the sample size. Okay, and what does this come out to be? Generally speaking, we go the same number of decimal places as the standard deviation. So 2 decimal places is fine. 2 decimal places is good. Okay.
Calculated to the point where it doesn't, like, put the square root on the bottom.
I'm sorry, say it again.
I said, how would you put it in the calculator with it giving you the right answer? Because sometimes it.
This times this divided by this is,
Okay.
yeah. This isn't one you can mess up. This one would be hard for you to mess this one up once you just hit the wrong button. Okay, so I'm going to go ahead and go take this screen down. Now that we have that, because that's all we need is this. All we need is love. So now we'll go back. So in our problem, again, for those watching at home, in this problem here, the n, right, what did we use for n? We used n of 60, we used an x bar of 47.8, and we used an s of 11.32. And since our error is Z025, because I said a 95% confidence interval, times the s over the square root of n. So we just said that was 1.96 times 11.32 over square root of 60. Again, in this example, and our x bar, I have it on the, so the people watching at home, I have it on the next screen. The x bar was 47.8. So what is the value that we get? What do you come up with? 2.86 to 2 decimal places. Now, what do I do with that number? Well, that would actually be 2.86 pennies. We said the average number of pennies somebody had in their pocket was 47.8. With 95% confidence, the true mean is going to be somewhere between this plus or minus this. That's the whole point of an error. It gives you a plus or minus. Now, compared to 47.8, that's pretty small, isn't it? That's not a big number. That's a good thing. We really like it when the error is small. So again, it's like saying, well, Robert's business next year is going to make $1 million plus or minus 10 million. That'd be kind of scary, wouldn't it? Because the minus would be really bad. You'd rather say you're going to make $10 million plus or minus 1 million. That would be better, wouldn't it? Because it's a smaller. Heck, $10 million plus or minus a penny. That'd be really good. But you want that error to be as small as possible. And the only way error can be small, twofold. Error can only be small if the standard deviation is really small, if you don't have any control over that, or the sample size is really big. That's why you want big samples, because you want accuracy. So for this problem here, for our numbers that we're working with, we can say that the true mean is somewhere between 47.8 plus 2.86, 47.8 minus 2.86. So let's calculate those. So what do we get here? You got a number? 44.94. 44.94 at one end. And 50.66. So we'd say we conducted a sample of size 60. We found that the average number of pennies people had on them was 47.8 with a standard deviation of 11.32. That means we had to collect all of our sample data. We actually had to calculate the X bar. We had to calculate the S, and those are our calculations. Now we can say with 95% confidence, the true number of pennies that a person has in their pocket, at Mesa College would be somewhere between here and here. Now that's not a huge range, so that would make you very confident that you got that one right. Okay, you with me so far? So where does this get used again? Well, in real life, certainly in any form of marketing, we want to know about our target audience. We want to know, people's consumer buying habits and things like that. But like I started by saying, you want to have a clothing store, but you don't have a lot of money to be able to fit every single person, big, small, and everybody in between. So what you want to do is target kind of the middle of the audience, right? You want to target, the mediums, if you will, but you need to know what is the middle. So you need to know what is the average of that group. So let's say we want to find the average height of a Mesa College student, okay? I'm being really, really vague in general here. The average height of a Mesa student. Now remember, this was the very first day of class. I used this example when we talked about how to do a good sampling. So we said, you probably don't want to make your sample just the guys on the basketball team, right? Or the people in the Hobbit Club. That probably wouldn't be a good sample either, right? That'd make us look really short. You would want a sampling where you went to different parts of the campus, different days, different times. Remember, we talked about how do you do a good random sampling? Let's suppose you have trained your staff well. And you have people going out there and basically, I'm going to walk up to you and say, Junior, how tall are you? You tell me and I'm going to write it down. Is that a good way to sample? Junior, how tall do you want to be? 6'4". All right, so Junior says he's 6'4". See, you don't ever do voluntary response samples because you're going to tell people what you want to be. By the way, if you ask people their weight, are you ever going to get the truth? Probably not. No, you can't do it that way. I'd say, Junior, can I measure you? Take a moment, can I measure you? And I get out my tape measure and I measure how tall you are. It takes me 10 seconds. I can't ask you how tall you are. See, my driver's license says 5'10". Because when I was in high school, I got to 5'9 3/4, I think. So my license says 5'10". I'm probably 5'9" at most right now, because time, shrinkage, and all that kind of stuff. And but my license says that, so I must be that tall. No, that's what I filled out on the DMV thing. my oldest son, his license says like 5'8" or 5'9", 140 pounds. He's 6'1", 200 pounds. But that's how tall he was when he got his license. So it's not what you wrote, it's how tall you are. So we went out, we're going to go out, we're going to train people, we're going to measure people. And let's say, do you want to do it in inches or centimeters? Okay, let's do it in inches. So let's just say we went out and we measured Mesa College students and we found out, we took a sample and we had time and we wanted to do this right. Okay, so we went out and we collected a sample of size, let's say 237. By the way, if this group right here said, we want to do this today, that wouldn't take us very long, right? Each of you would do, 30 or 40 people over the course of a couple hours. That'd be easy. So we went out and we collected a sample of size 237. We found out that the X bar was, let's say, 54.3. Units are important. And the standard deviation was, let's say, 4.71. And that's also in the same unit. One of the reasons we use standard deviation instead of variance, variance is the square of standard deviation. So the units of variance are the square of the units that we're measuring in. We're measuring in inches, mean is in inches, standard deviation is in inches, but variance would be in inches squared, which isn't useful, is it? I need it to be the same unit. So you went out and you collected this data, you are pretty happy with the way you sample. And what I mean by that is you believe you did not conduct a biased sample. You got a good cross-section of students, day and night, different days of the week, everything, right? You didn't make 90% of your sample men. You tried to keep it roughly the same because you believe the population of Mesa is pretty close to the same. And I don't know what the population is, but I'm sure it's pretty close to the same number of men as there are women. So your sample should reflect that. We did everything right, we got this. So now here's the question. Based on this, I want because I want to really be certain we don't miss anybody. I want a 99% confidence interval. I want a 99% confidence interval from you. Well, I've got every number but one that I need. What's the only number that I still need? Again, error is the z of, we call it alpha over 2. The reason they call it alpha is the tail probability. So in a 99% confidence interval, alpha would be 1%. It's how much is in the tail, but isn't half in each tail? So that means I want 0.005. So in this case, that means I want 0.5% in each tail. That's what that means. A 95% confidence interval, you wanted 2.5% in each tail. And if I said a 80% confidence interval, then you'd want 10% in each tail, on and on and on and on. The reason it always says alpha over 2 is to remind you, oh, I got to cut my tail in half. It's half in each tail. I need to look up this number set. And it's this times S over square root of n, remember. So what is this number? Okay, it's on your sheet and it should be in your notes and you should have it written down. Don't memorize it, but you should have it available. What are those four magic numbers? Beautiful. 2.576. We looked it up on the table. I put it down. It's in the notes. It's on the formula sheet that you're going to bring with you next week. Times S over the square root of 237. That's a big sample. That's good. That's a big sample. It means I have a lot more trust in whatever I get because my sample is so big. Even if I got the tallest person on the campus, even if I got the shortest person on the campus, with a sample that big, is one person going to make a huge difference in the mean and things? No. No, if I only grab two people, and the one was the tallest person, yeah, that would be a little bit skewed. All right, so what do we got? 2.576 times 4.71 divided by square root of 237. Got a number? So if we're going two places, what would it be? So 0.7. Boy, that's a small error, isn't it? I like that. That's small. Again, small cushions are better than big cushions. Small cushions are better than big cushions. So now when I answer the question was, what is a 99% confidence interval for the true value of the mean? Well, the true value of the mean, therefore, let's see. I guess I'll put it right here. The true value of the mean will be between X bar plus the error, X bar minus the error. But the error is only this much. Boy, that's wonderful. If we could only be so lucky in real life. So I've got the mean is less than 55.09. And 53.51. So we went out, collected a sample of size 237, and found out our sample mean was 54.3 inches, and our sample standard deviation was 4.71. We can say with 99% confidence, the true average height of a Mesa College student is somewhere between 53.5 and 55 inches. Will that help us now if we want to design our own clothing line to fit the masses? Yeah. That's the whole point.
Did you remember me again for your 0.005? Wait, while we have to look into that.
Well, we already did that last week, and so we have those numbers written down. Those were the 4 magic numbers. You remember? I mean, you have them in your notes. You have them on the formula sheet. The base right here.
Oh, okay, it's in the form. Okay, I see.
Yeah, those 4 numbers you don't memorize. We have them. We use the same lines in the sand over and over again in stats because we kind of want uniformity. When you have a whole bunch of people doing similar things, you kind of want to do it the same way. There's no right answer to this question in terms of what is the right confidence interval. I want to make sure that I don't miss anybody. This means that of all of the samples I could have possibly taken, 99% of all the possible samples that exist, the true mean would be in this range. Is it humanly possible that I just happen to grab too tall of a group or too short of a group? Is that actually not possible? Yes. What is the likelihood that it was? Only 1%. Because that's what the 99% confidence means. I got 99% of all possible situations. I'm pretty happy with that. Okay. When do you choose 99 versus 95? Because most of the time confidence intervals are 95%. That's kind of the universal standard. There's no such thing as 100%. Because that would mean I'd have to have every human being on planet Earth, that kind of thing. If it's something like a rare disease or something like a cancer diagnosis or something that could be life and death, you want a bigger confidence interval because you don't want to take a chance that you missed somebody. In other words, you don't want false positives we can live with. Do you know what a false positive is? If you're being tested, let's say for a disease or cancer or something, a false positive says you have it and you don't. And then you can always do another test and then it would say you don't have it. You're scared. You're terrified, but you're okay. What's way worse, a false positive or a false negative?
False negative.
False negative means you have the disease, but it didn't show up. Therefore, you're not going to get treated for it, and therefore, bad things. I knew somebody who had a false negative with cancer diagnosis, and when they finally diagnosed the cancer, it was a little too late. They just whiffed on it. No, you can live with false positive. So the false positive is because the test is showing everybody, even people that don't have it, it's just close. You want a test that is so sensitive that if there's even a chance that you have the disorder or the disease, you want it to show up. That's why you can get false positives. You don't want to test, I don't want anybody to feel bad. So I don't want my test to be that good. That way I don't want any false positives. I don't want anybody feeling bad. Well, if you have no false positives, then you don't have a very sensitive test. And you're going to miss a lot of people. You have false positives to avoid false negatives. That's what it means. Your test is so sensitive that you get people accidentally. But you can live with a false positive. Okay, does everybody understand that? You can live with a false positive. You probably can't live with a false negative because that means that we missed. So that's in the medical field, they often go for the 99% because they just don't want to take that chance. But in just everyday life, in things, 95% is usually good enough for a confidence interval. Okay, let's do another. All right, so let's suppose we, for Mesa College students, let's stick with Mesa College students because we have a really large population. I would like, I've heard that Mesa College students just make fantastic basketball players. Everybody at Mesa College, because Mesa College, we have hops, right? As a collective campus, we have hops, right, Lila? You can get up, you can sky, can't you? You like doing those gorilla two-handed backwards dunks. So what we want to find out is what is the average vertical leap of a Mesa College student. Now, what's a vertical leap? Did we know? That's not a trick question. The term vertical leap means yes. So do you get a running start?
No.
No, it's how high can you jump from a static standing position. It's just literally jump up in the air. And that's, you've seen they have the little bars, and you go up and you slap them and you touch them. It's really easy. I don't have to measure anything and just see the bar I touched. Oh, okay, that's how high. So what I do is you measure how high I can reach. And then whichever one I can reach, that distance is, it's pretty simple, right? It's not rocket science. So we want to find the average vertical leap of a Mesa student. They're going to exclude the instructors because, we'll really skew the data, because the teachers can sky. Now, we went out there, we collected a huge sample. We collected another big sample because everybody wants to do this. In fact, Robert set it up out there. He's got his big pole with all the little, I don't even know what you call them, the little marks, for each of the different heights. And people want to just walk by and slap it and spin them. If you've ever seen one of those, it's fun to just slap them. So you got people, hey, everybody, you want to find out your vertical leaps? You've got a line. It's a really long line. And by the way, how long would it take to measure someone's vertical leap, you think? Seconds. So can we go through a lot of people? Oh, yes. Yeah, in fact, right next to like the dunk, booth, and like a fair. So Robert goes out there and he collects a sample of size 1,278. He got a lot of people. Everybody wanted to have their vertical leap measured. But you got a lot of folks who have lead weights in their shoes too. Right? You have people who could sky and people who, couldn't. So let's say the X bar you came up with collectively on campus, let's say was 18.7 inches with a standard deviation of how about 5.32 inches. So here's what we want to do. We want to construct a 95% confidence interval for and we always see it this way, for the true mean. This does not mean that this is the mean of the campus. This is the mean of my sample. Yeah, by the way, this is a big sample. This is a huge sample. Would you say the most likely mean of the college is the mean of the sample? Yes. The most likely, when we shot free throws last day, the most likely probability that you're going to make a free throw is what we actually witnessed when you shot free throws. That makes sense. If I'm flipping a coin, the most likely probability of it landing a tail is what I just viewed when I flipped the coin a whole bunch of times. That's the most likely outcome, but it doesn't mean it's absolutely going to be the outcome. That's why we like the cushion, right? We want a plus or minus. So next year, when predicting the outcomes of our business, let's say, well, how is our business going to do next year? Well, we don't know that. We have a pretty good idea based on this year, but it'd be better if we had a cushion, a plus or minus, right? Things could be better than we thought they were going to be. They could be worse than we thought. So with this information, constructing a 95% confidence interval, well, that's now trivial because we have all the numbers in front of us. We just have to do a simple calculation. Exactly. So because we want a 95% confidence interval, we are going to use the 2.5% tail. That's what that means. And that would be the 1.96. Okay. So with that, there is 1.96 times what?
5.32.
Times 5.32 over the square root of 1,278. So let's calculate that. And 2 decimal places will go.
0.29.
0.29. Now, what does that mean? And again, that's inches. Well, because we took an absurdly large sample and we don't have, I mean, our standard deviation is not trivial, but it's, I mean, standard deviations are not zero. If every single thing you measured was exactly the same, if everything you measured was exactly the same, then the standard deviation would be zero, wouldn't it? Because you're not moving. That's not really possible in any scenario, okay? But if our standard deviation isn't huge, then our errors tend to not be very big. But more importantly, our sample size was ginormous. So therefore, our error is tiny. That's a great thing when your error is tiny. So what can we say with 95% confidence? Now we use X bar plus X bar minus. Okay, and this is our confidence interval for the true value of the mean. So let's do this. So what does this come out to? That's a 21.
18.41.
And 18.99. So that means with 95% confidence, the true leaping ability of a Mesa College student is in this range.
Did you use a calculator?
Not for that.
I saw it. I was like, I see.
I use a calculator for that. Okay, you guys with me? Is this complicated?
No.
Oh, heck no, this is easy. But confidence intervals are so important. So let's remind ourselves, why are we even doing this? Okay, I want to make conclusions about populations, but I only have samples to use. The best number that I can use for a population is whatever my sample is. But the chances of that, that's exactly what it is, right? I'm going to measure a certain number of people and use them to do my whole population. That's a little iffy, isn't it? But if I use a large enough sample, we're now saying, oh, the confidence interval is not going to be that wide. So whatever your sample mean was, the true mean shouldn't be very far away. Now, we're making a huge assumption here. We're assuming we did a good, proper, non-biased sample. So Robert was a little short for time, so he didn't have time to do a huge sample. So he figures, I'm just going to run by basketball practice, and I'm going to measure those guys' vertical leap, and I'm going to use them to represent Mesa College. Good idea? Terrible idea. Yeah. Wow, the average Mesa College student can jump 30 inches. Yeah. They should all be in the NBA, all of them. Again, that would be a horribly biased sample, wouldn't it? You see, you can't do it that way. So assuming that we did everything right, and that means we have a non-biased sample, that's the assumption I'm going to make, because we started the course talking about how do we properly sample. Now that we understand sampling, and we have a pretty good idea of what it would take to do a good sample. Now, let's suppose now you would like to know what people spend. Let's say you'd like to know what people spend each time they go to the grocery store. In fact, let's make it easy. You would like to know what people spend at one particular grocery store. It doesn't have to be any particular. It could be Trader Joe's. It could be Ralph's. It could be Sprouts. I have a Sprouts by my house. I'm there all the time. But you would like to have an idea, what does the average San Diegan spend, or what, on average, I should say, what does a San Diegan spend when they go to that grocery store? Now, if you don't ever go to that grocery store, then you won't be counted in the sample, would you?
No.
So how can you do that? Well, let's just suppose that you're sitting in a booth, or you're sitting in a chair right outside. Now, I don't know about you guys, but usually when I'm walking out of a store and I see somebody sitting down, it's because they want money, right? They want to collect something from you. But other people, when you're seeing people there, they want you to sign some petition. That's the other thing people do. But you actually, maybe you're standing, rather than outside, you're standing at the door just saying, would you mind if I looked at the total on your receipt? I'm not interested in what you bought. Would you mind if I looked at the total? Now, would everyone say yes to that? No, but would people say yes to that? Yeah, you're not offended. Oh, okay, I spent $13.47. They just want to see the total. They don't want to see what you bought, because we're trying to figure out how much money do people spend. Now, this is a tricky one, because not everybody's going to be agreeable, but if I did this over the course of several days or even several weeks, could I get a pretty big sample? Sure. And how long does it take me to collect the data? Like before, seconds. It takes seconds, and it doesn't cost me money. So let's say that you chose, I'll use Sprouts as an example. So you found a whole bunch of Sprouts in San Diego, and so you hired your crew, and you say, I want you to work there, and it doesn't matter what time of day, maybe go at a fairly busy time of day just so you can get lots and lots of people in the course of an hour rather than 5 people. I'd rather get 50 people in an hour. Does everybody follow what I'm doing? So we're going to go out and do this. By the way, these things do happen because when you're watching the news and they talk about how much money people are spending on groceries and things like that, how in the world would they know this type of sampling? So you want to find out how much money is spent by each shopper, let's say at Sprouts. And I don't mean over the course of a week or a month, how much money did you spend? I mean, how much is spent each time you went to the store. That's actually way easier. So what does a person spend on average when they go to the store? Because then later I can say, well, how many times do you go per week? See, I do the same sort of thing. I go to the same stores pretty much the same time every week. You know, my wife goes to Costco every weekend, you know, and that's the biggest one. I go to Trader Joe's every Friday morning. You know, I have certain routines that I do. And so it's really easy. If I knew how much I spent on average, then it's really easy for me to look at what did I spend over the course of the year or the month or whatever. So you're going to sample. You would like to know how much money is spent by each shopper at Sprouts. And again, you want to do this not at one store, you want to do this at many stores. What's wrong with only going to one store? Well, first of all, do you have a cross-section of San Diegans? How many go to Sprouts? I'll just give you. Okay, who goes grocery shopping ever? Okay, what store do you like to go to? Okay, so do you go to every Walmart in San Diego County, or do you go to the same one? Yeah. That's the problem. See, if I only go to one store, then I'm only going to catch those people who go to that store. I'm not getting a cross-section of San Diegans. That's not a good sample. That's like saying I want to find the average height of a Mesa College student by visiting one class and measuring those people only. I kind of need, so that's why I'm saying, if we're talking about, I'll use Sprouts as an example because I shop there. I would like to get 10 or 15 Sprouts. I'd like to get them all over the county. So then I'm more likely to get customers who live all over the county. Because I don't know about you, but I only shop at that one Sprouts. My wife only goes to one Costco. I only go to one Trader Joe's. And I go to the same one every time. So most of you shop that way. You go to the same store because it's convenient. Why would you drive across town? Now, if you were across town, you might say, I'll go to that one today because I'm here. But you wouldn't make the separate trip, would you? That doesn't make any sense. So we want to get a good idea of how much money people are spending. And so what we do is we went out and again, we collected a lot of information. And let's say our sample is, you know, people were not entirely willing to talk to us as much as they were, you know, to measure their height. So we collected a sample, let's say, of size 97. We found the average amount a person spent was $53.47. That would be $1. But in this case, there was quite a bit more variation because one person went in and bought one item. I always laugh when I go to a store and I see a person with one item and I've got, you know, shopping cart full. You went to the store for one thing. I don't think I'm physically capable of one thing. I can just go through the fruits and vegetables and fill up the basket. But you'll have the person who bought one thing, you'll have the person who spent $200. And they could be back to back in line, couldn't they? So what you're going to see here is a much, much larger standard deviation. So here, let's say the standard deviation was $22.18. Okay, it's way bigger standard deviation because this one really has a much bigger range. So this time, because it's not life and death, let's construct a 95% confidence interval. So what Z are we going to use again? 0.25. And again, how do I know? Because a 95% confidence interval means you have 5% in the tails, but that's a total of 5%. So that's 2.5% in each tail. So the Z that corresponds with the 2.5% tail, that's why we write it this way, is what? 1.96. I have all of the numbers I need to do my calculation. So the error is, tell me, what am I going to put in my calculator?
1.96. 22.18. And then
Square root of 97. Good. Now this is a dollar amount once again. What do you have? 441. Probably a little big.
I figured out what I did.
You did 196, didn't you?
Yep, I did.
So what should it be?
44.1.
No,
I don't know the decimal places.
4.41,
Yeah.
which is what? $4.41. Now, this is why I'm putting that. It's so important that we understand these things have units. It's not just a number, it's dollars. Oh, the average amount of our sample was in dollars. Our standard deviation was in dollars. Therefore, the error, the plus or minus we're going to add to our X bar must also be in dollars. I can't add inches to dollars, can I? I can't add, number of cats to dollars. I kind of have to add dollars to dollars. So I say that kind of jokingly, you have to have the same units and you can't combine them. So my error is in dollars as everything else in the calculation. So what am I going to do? It's going to be this number plus or minus this number. And that's where the true mean lives. So then we can write that out. The true mean is between this number plus this number minus, and we'll put the units on in our answer. So what do we get?
So for the minus, it's 49.06.
And for the plus, it's
57.80.
so based on our sample, we believe that the average a customer spends at this grocery store every time they go, on average, people are spending between $49 and almost $58. Sound reasonable? Yeah, that's not the worst thing in the world. All right, what I would like to do now, because I think you guys got the hang of this, I want you guys to work on the quiz right now. Okay, so I'm going to bring it up. Oh, shoot, hold on, I got to put the screen back on again.
would that be quick 16?
Probably. I don't have them memorized, but because we can do this. A lot of times we wait way too long. We wait too long to do the stuff. You guys have it right now, but you'll wait till next week to do the quiz, and then you'll only have problems again. Now, does everybody have? By the way, you don't need these, not for what we're doing. What do you need? You need the magic numbers. I'll write them down again. Well, actually, I'll leave them out here. You guys you can look at them. I have a couple of extras here. Okay. Taking back to the same teacher. Okay. Firefox. Just for the Z values. That's all you need. Because you guys should have the formula down by now. All right.
Yeah.
GPT. Wait, no, this is not quiz 16. Hold on, you said quiz 16. This would be quiz 16. This would be quiz 17. Yeah. Quiz 16. Well, we can go back and look at quiz 16, but
Was that?
that's what's due next class. Yeah.
Last class.
Yeah. Well, let's look at 17 now, and then we can go back and look at 16 afterwards. 16 is on the exam. 17 is not. 17 is on your last exam.
So, quiz 17.
Yeah, this is today's lecture. If it ever comes up. This computer really doesn't want Firefox because Google Chrome is sort of the default browser on this campus. This is not giving me, hold on, this is just giving me issues here.
What's our next exam?
Tuesday.
Of next week?
Yeah, you guys do have a schedule, don't you? All right, this is not letting me. No. Yeah, this is kind of annoying.
The diagonal arrows maybe?
No, when I hit this, it should show up in the lower left corner and to open up. It's not. This is really, yeah, I said, I don't use Firefox, like as in ever. There we go. This is ridiculous that it's taking this long. All right, so does this sound familiar? I'm not even giving you a situation. I'm just giving you the numbers. You have a sample size 25, X bar, S, construct a 95% confidence interval. And then the next question, you have a sample of that. I'll leave them both up here. So let's see if we can figure this out. These are pretty short and simple questions, by the way. We just did like, what, 10 of them or something. Okay. Yeah, 60. Keep going. Keep going down. Okay, why do you know that? Yeah. Did you look at the lecture on Zoom?
Yeah.
Okay, did that help?
Yeah, I mean, I understood it.
It's not a perfect situation, but it's better than nothing because we always have people asking. We don't ever have everyone here. For whatever reason, we can't get everyone here. Well, why don't you try this? How should the answer look? Your final answer should look like something less than mu, less than something, right? It should look like an inequality with the mu in the middle. Yeah.
Was it, if I did this correct?
So then, yeah, and that's, the whole point is you're saying, based on that information, this is my conclusion, that the true mean is somewhere in there. You're not saying the true mean equals. You're saying it's in this range of values.
That's what you said.
And that's the proper way to say it. Again, if I'm only taking a sample, I can't know the true mean. That's not possible, but I can be confident. How confident? I'm 95% confident. What does that mean? That means there's still a 5% chance I missed the mark. That's what it means. Is there such thing as 100% confidence interval? Yeah, you measured every single thing. So I want to find average human heights. I measure all humans right now. That's the only way I can be 100% certain, but that's not actually possible. Does that make sense? Okay. Now, are there ever a situation where we have 100%? Yeah, the census. That's it. And what is the census? That's where they actually count every single person in the US, and it takes a year to do the census, which means at the end of the year, that information is actually no longer accurate, is it? People have been born, people have died, people have moved. That's the irony about a census. So when they finally put, entering every city in the country, when you enter the city, it says, you're entering city limits, population of the city. How often is that population updated? Every 10 years. Because that's how often you do the census, every 10 years. That's what I'm saying. When they're finally done collecting the census data, which takes about a year, these numbers are already off, aren't they? Oh, so that population that says, this is the population entering, that was true for like 1 minute. A few years ago, yeah.
So pretty much like the way like just drop like that in like a something like that.
Well, let's hope it doesn't come to that. Yeah, I'm not into,
I know, but the way how it's.
Thanos is just not a really good.
It's just gonna say that you don't have years, so I think,
Yeah, because the census takes so long to collect all the information, literally takes an entire year, then we literally have every household in the United States. But over the course of the year, things do change.
So we're going through the review this Friday, correct?
Oh, yeah. Okay, you get come. Today, Thursday, new material towards exam 4. We've already had the 5 lectures that this test is on. It finished last day. So this Friday will be our Zoom review. We'll do like we've been doing, we'll do the, and the reviews have been taken pretty much the whole 2 hours, by the way, which is fine. But when you come to the review, you have to have already done the practice test. It does you no good, right? You have the practice test, you have a key. What good is it to come to a review and watch me, put the key up that if you haven't already done the problems? You've got to do the problems. So then, Destiny can say, well, how did I know to do this and not this? Or I was stuck here. Can you show me what should I have done? Could I have also done it this way? These are good questions to ask. Not, can you do the problem? I've never done it before. Can you do it for me? Well, you have a key. I've already done it on the key. So it doesn't do you much good if you haven't tried the practice before you get there. You know what I'm saying? That it's kind of a waste of time. And then that's the affirmation that, yes, I know what's going on. Because the other thing is the calculators. A lot of us are still struggling with entering things in the calculator. Now, these calculations have been pretty simple. Now, you guys got these?
Yeah.
Feeling pretty good?
Yeah.
All right, let's go to the previous quiz then.
Was it 15?
Hold on. What did I say? No, 16. Let's do the confidence interval for the P's. Now, this one is very similar. Now, this is what we did last day. This is the one where right? It's right in front of you. You have your N, you have your number of successes. So you can calculate your P hat. And then you calculate your error based on this. So it's very similar, but now we're doing a confidence interval around P. And that was the entire Thursday lecture of last week, if you remember. Okay. So in this case, what was the error? You remember? It was the magic Z times what?
Sure.
It was P hat, Q hat, N. What is P hat and Q hat? Well, it was the measured probability. It's what I observed. I like to say that though, it's what I observed. So you flipped a coin 100 times and you got 57 tails. Your observed probability was 57 over 100. That's what you saw. And you're using that then to figure the true probability. So in this case here, it says of the 500 people, 285 are what we're counting. So my measured probability, my P hat would be what? 285 over 500. What's Q hat then? What's Q hat always? Just whatever's left. What's Q hat is whatever's left to make it add up to 1. So Q hat is just 1 minus P hat. It's always that. Remember, P hat and Q, P and Q, P hat and Q hat, they have to add up to 1. P hat is what you observed. In the next problem, he makes 83 of 100 free throws. So what's his P hat? 83 over 100. Now, what's the most likely true probability? That number. But is it possible that he was a little bit better that day than usual or a little worse that day? Yeah, that's why we put a cushion on it. We put a plus or minus. Now, in terms of the magic numbers, we use the same ones, right? And those are the two over and over and over again. So let's try those two.
Present.
Yes.
You can help me on number 1. I'm so good.
You take notes because we did like 10 of these in class last day. So we did all these problems in class.
Oh, no, I do just.
So, well, go back to the last one. Go back to last week. It's not way different. No, this is still today. Did you write anything down last week? Okay, this was for sample size, so go back a little bit for. Yeah, so we're doing stuff. You wrote down the formulas, but you don't have examples. So you want to make sure you have. Can you see that one with the numbers?
Alright, so you can look at it probably.
We have all the formulas. And have all this, we did all these problems in class last day. See again?
And then.
Yeah, your number, your probability. And then the probability figure, whatever.
I'm with you. Oh. Give me on Thursday. Okay?
Okay, they're done, Denise.
Yeah. Give them to me on Thursday.
And I'm telling you right now, I know my schedule is never gonna change. I'm the only one that does closing shifts.
Mm,
And so
where do you work?
I work at BJ's.
BJ's. Is that a restaurant?
Yeah, it's a brew house.
Which one?
The one,
Is there one in Escondido?
yeah, it's the one by the North County Mall.
You work in Escondido
Yeah,
until midnight?
I live in Escondido.
Oh, okay. Yeah, we went there when I think youngest son had his 8th grade promotion. I think we went there.
We have a lot of kids that come in for like
things like that.
And no, I just remember I really enjoyed it. It's the one time I went there, and my son had a friend who was working there at the time. I can't remember her name.
I get free food after every shift. So I get off around 11:30. So by the time the food's done, it's midnight. I have to go home and I have to eat soon because I haven't eaten.
You can't eat at the restaurant?
Well, we close at midnight, so I'm not gonna. I need to eat when I get home, and I have to get myself ready for bed, and then by the time I get myself ready, it's like 1:30.
All right, everybody, let's hammer these out. I don't mind if you talk to each other. I'll say you might want to talk to Lila to help you set this up. It's pretty good, Justin. So what do you got so far?
So for P, so you said 285.
Okay,
And then,
what's Q? Well, think of this as free flow if you want. You made 285, so how many did you miss?
is it so connect to the 500 like remaining?
No, how many did you miss? Yeah,
Probabilities.
I just thought about this. I gave you my quiz that you called.
yeah, I've got a stack of my, I keep forgetting, I'll get
Make
them.
sure that you got it.
I've also got like 20 or 30 that have graded that people haven't picked up. I had to stack. I will bring them. I apologize.
Okay.
Yeah, I get a little bit behind sometimes in terms of paperwork.
You're talking about being behind. I mean,
Yeah.
But at least I understand the stuff, so I'm not like confused.
Yeah.
1.96.
It's okay.
It's still time.
Yeah, I clicked on that, and then
On the top
Oh, no, yes. Oh, yeah. Square root.
and probability. I mean, you can. I mean, when you.
And then 100, 500.
These questions are going to show up on the exam. You want to know that you can do them because they're not long. They're actually kind of simple.
I want you to know that this right here, and then using those notes, I read weekend in any math class, I've ever done.
How come
Multiple to do
you don't like taking notes?
No, I'm just really bad at it, so like, I
Well,
have.
probably not taking notes, just relying on remembering every single thing off the top of your head. You don't take bad notes. Notes are useful. The idea of notes, you're telling a story to yourself of how to do stuff. So that when you go back and look at it, you go, oh, okay, I know what's going on.
Oh, for
But if
the.
you don't write it down, the chances of remembering everything are probably not really good.
I don't know. But I guess it. Let me make sure before I call you something on.
You got something meaningful here? All right, so. Good, that's what it's supposed to look like.
Okay,
So what are you asking?
The setup is correct.
Yes, no, all you gotta make sure is that you did the numbers correctly in your calculator.
Oh, yeah, I did.
Now, you answer, you go, okay, yeah, that's reasonable. If that was some astronomically large number, or you know, you got a bazillion zeros, you go, man, that might be a little bit iffy, but this is correct. This is where we all have problems, is the actually entering in the calculator. Your calculator's pretty friendly in that you can see. That's important. You can see what your calculator looks like is exactly what you're looking. That's critical.
So would it change it if I had divided these beforehand and then put them?
You mean,
Like turn these fractions into decimals?
no, wouldn't have been any different.
Okay,
Wouldn't have been.
but that would just.
Because that's a terminating decimal, you can certainly enter it. Well, what if your denominator was 497? So you don't have a terminating decimal.
Yeah.
Then you got to enter as a fraction because there's too much round off otherwise.
So it's safer to go.
Yeah, way safer. Okay?
Yes, you can.
No, this is not, This is completely unrelated.
Part as it
This
does.
one?
This has nothing to do with today's lecture. This is last, this is P, this is this. You're doing,
I don't know how to.
you're doing an interval for the two probability.
Yeah, this.
This is 0.57, 57%. So your answer is gonna be that number plus or minus, P hat plus or minus the error. That's, so again, this is, you have it in the notes, and in fact, Destiny has it in her notes. It is, it's this right here. This is last case lecture, this stuff right here. The measured probability plus or minus, so this would be decimal number plus or minus, and then that was the error.
So,
So you're not using 285, no, you're using,
that doesn't point to these ones,
yes, yes.
So, Samantha?
but was this part correct though? Right here?
No, this not even similar. This is supposed to be a probability, 21. It should be a tiny decimal, in other words. Because you're not using 285, you're using 285 over 500. That's the number you're using.
This is not working.
So it's not. Because we're supposed to use the decimal version. We're using the actual number.
Well, you can leave it if it's over 500. And it's what it's about. So it would be.
So did this look right?
Oh my.
You think?
I don't know if it's how you. It doesn't matter.
Yes.
About
Give me 1 second. My daughter contacted me.
Yeah, I don't want that.
So what is this? This is your error? Good. So now what do you do with that number? It's this number plus or minus that number.
You got it? What do you think?
0.01.
0.0421.
Usually, remember with probabilities, the standard is 4 places only out of convenience. There's nothing wrong with going more, there's nothing wrong with going less.
You got around that. The last seven.
And remember, because the tables we look at always have 4 decimal place probabilities, we just sort of keep that as the norm.
0.04. And then you take a.
Now you're gonna say, what is your p hat? No, 285 is not a probability. That doesn't make any sense. That's a probability. And it's not p, it's, you don't know what p is, you're trying to find an interval for p, so it's, but it's over 500. Think of it like free throws, 285 over 500. You don't say my percentage is 285, you say it's 285. And then those are the by the way, the 500 is supposed to be inside.
Yeah, and I think.
Yeah, that's important. Well, no, because people will make that mistake when number. So that's p hat, that's q hat, and therefore my error, I'm going to take that number and go plus or minus. Well, on this one here, what's your p hat and your q hat are identical. P hat is going to be 285 over 500. You can think of those like three. You made 285 over 500. So how many did you miss? That's what you got. And now you can calculate the error because that's the formula. Or the number. Now, notice in the problems, the first one I asked for 95%, second one 99%. So you're not using the same z.
0.005.
It'd be the z with a, yes, with the 0.058.
2.576.
So what is your answer?
Greater than.
You're going there. What's the confidence interval?
Yeah, less.
You're finding a confidence interval.
How am I not getting?
So another word.
When you,
It's not, that's not P and Q, those are measured by P. If you did P, you wouldn't have to do both. Right? You're saying, oh, I took a C, and that was going to simple. P has like X bar. And,
oh, you know what you're doing?
this is the sample stand, so P and Q map.
Yeah.
They show
It's not the 500.
P, yeah, and so what I'm gonna do is say, well, there's my error, that's a probability.
Oh,
So it's gonna be that number, plus or minus.
And then it'd be, yeah.
Oh,
it has
okay.
to be, it has to be a fraction.
So you can write that as a
So
decimal.
this plus or minus.
Square root.
Yeah, I mean, well, you can put it on okay, oh, shit, you should talk to Ryan, she's got this down, she can help you out. So what's, an 83? Oh, Phil.
Yeah.
So you're saying the true probability is somewhere between there and there. Now, in terms of round off, it's usual because when you calculated this is a probability. So usually probabilities will go 4 places.
Oh, okay, I see.
Why? Because the tables, the reason we generally, by the way, it's not a rule.
So when I'm getting.
These are all probabilities and every one of them is 4 places.
I see.
That's why we say, you know what, if we just say every time we use a probability, let's report it in 4,
Okay.
then we have a consistency, so it's easier to go back and forth between tables. There's nothing wrong with what you wrote,
Oh,
but you have enough information to go more decimals. That's all.
but this is not correct, so. the-
Yes, that's what you're wondering. But, oh, because well, you have a 0.52. Which one are you on? The
The
first or the
the
second?
first one.
It's not 0.52. What's 285 over 500? The problem is you have that, it's not 0.52, it's 0.57.
Yeah, my bad. I probably saw that. It was a 7 now too. I didn't write it right. Oh, yeah, I wrote it. Yeah, I just wrote this one.
It is, by the way, it is absolutely correct to use the fractions. But if those fractions give you a terminating decimal, if you have 1/3, don't enter 0.33, you're rounding it off, enter 1/3. But 285 over 500 is the terminating decimal. And so from a calculator standpoint, it's easier to enter the decimal than use the fractions. Do you agree? Now, in the problems we were doing before, no, we had to enter them as fractions because none of those were going to be terminating decimals. You know, I just gave you random ends. But in both of these cases, 83 out of 100, that's 0.83. That's easier to work with.
Pretty good.
And this is,
Like I said,
that's what it should look like.
And this can't be-
So the true probability, we're saying, is somewhere between those two.
And this is gonna be on the.
Oh, yeah. Yeah, this was Thursday's quiz, but it's also the last material on the exam, which is why I want to make sure you guys can do this. This was last day's lecture, but it's not the same as today's lecture. Does today, what's that sound? Okay. Somebody below.
The calculation like that.
The calculator still what?
I gave him
Well, what did you do? You're showing, do the whole problem. So what is going into calculator? Well, here's half the problem. That 500 is supposed to be inside the squares. You got outside square. See the formula? That matters. You always get a different answer.
It can't do like, it can't be like a whole problem. It has to be-
So you can go square root parentheses. That would be the same. And then do this times this divided by this, close parentheses.
oh, that's fine.
See, right now your 500 is outside the root, which is going to be a very, very different answer. It's got the inside. That is an interesting looking phone. That's your phone case that looks like a lot. Okay. Well, that's kind of cool.
Are all our exams on Tuesdays?
Yes.
That's good, because I have Mondays off, which means I won't be burnt out.
So how are we doing, folks?
It's,
Are we pretty good?
yeah,
It'll be better.
It could be better. How could it be better? I'm gonna go ahead and close this for the next person. All right, well, we got an unbelievable amount accomplished today, people, which is very cool.
you got them? Yeah.
All right. Yes.
Okay, well, first of all, I'm missing the point. We're doing it wrong, but not really similar to the other. The question is why confidence symbol around P, not around 285, but around this fraction, so it's not X. Define confidence-
You're trying to do today's lecture on this.
This is last day's lecture.
Defining confidence intervals around P.
Okay.
Yeah, and here, I'm not sure what you do, but if your P hat, what is your P hat? next to it? Yeah, but P and P hat are not the same. That's like saying U and X bulk. One's the population, one's the sample. It's been actually impossible. You're using one to estimate the other. So you're using this to estimate the true probability. So your probability is going to be this number plus or minus this number. Sometimes you don't kind of want to. 0.83 minus that is still not that close to 0.83.
Oh, where did I? Okay, I used to be on accident.
It's still.
Well, I think you also have it.
Yeah.
You're doing crazy now. Yeah, do you have notes from last week?
Yeah, I do.
We did all these problems last week. And they're exactly what we did last week.
I think I just.
So you said it's not, won't be correct if I come on the fourth one?
Generally speaking, we like to go 4 on these. Now, what's 83?
That's the,
No, it's not.
for the ball for number 2.
He made 83 out of 100 free throws.
Oh.
83 was how many he made.
I said,
If he made 83 out of 83, then it's 100%. And that number's got to be in the square root. Again, you've got it outside the square root, which would be very, very different. That square root's got to include the 1. The square root's got to include the 1. This is in the square root, not out. See the formula?
yeah.
If I put the n outside, it's not even close mathematically. It's a million miles away.
So it has to be like 100.
Which one?
Oh, okay, I see.
Having the square root stop here is not the same number. If I divide by a number and I divide by the square root of the number, I'm not the same.
Okay.
Yeah, you've got to make sure you're writing. That was the mistake that June made. He had his 500 on the outside of the root and it was giving him the wrong number. That's why you got to have it on the inside.
When I.
That's why that's the formula right there. Okay, well, you guys hopefully are set up now for Thursday. I'm gonna go ahead and stop recording.